Well, 5 years later, thank you, Mikhail, for being here. Mikhail works at Pinely, and he's going to talk about something that really interested. So the long road to const. So thank you very much, Mikhail, for being here, and the floor is yours. Thank you.
Thank you. Hey, all right, thank you everyone. Thanks, Jose, for the introduction. I actually do remember our conversation in the main list, and the idea was, okay, maybe Spain is a pretty hot country and COVID doesn't like hot. Maybe it won't go there. No, it did. All right, so the title of the talk is Specifiers, Qualifiers, and the Long Road to Const. A couple of words about me. My name is Mikhail Matrosov. I currently live in Amsterdam. I'm a tech lead at Pinely, which is a proprietary high-frequency trading firm, and I develop a trading system which automatically trades all kinds of assets on all kinds of exchanges all over the world. And to give you a sense of the scale of latency on which we operate, I remember that a couple of years ago I was actually implemented a task that I had to change the reporting of our internal metrics of the latency of our system to switch it from microseconds to nanoseconds because microseconds didn't tell us much. Most interested intervals were mostly 0 or 1 microsecond. So we had to optimize below that. All right, now today's talk, it actually started, the journey itself started quite many years ago in my previous company at a code review where there was basically a senior software engineer was declaring a constant which was constexpr, and I just added a remark, okay, maybe you also made it static. And then there was a misunderstanding. Why should I mark a constexpr static? Constexpr is something that should exist only at compile time. What would static mean in this? And then there started a conversation, which is irrelevant, but it actually nudged me to embark on this journey of exploring what the hell does it actually mean, and what do all the specifiers and qualifiers in the language mean. So we will have this like guiding example, I would say, that would carry us through this talk, and I invite all of you with me on this journey and exploring specifiers and qualifiers in C++. I genuinely tried to stick in as many as I could in one definition. So I believe there's not more you can do. And I believe that by the end of this talk, we will be able to untangle this monstrosity and actually understand what should it mean. And then while this journey, we actually will be able to come up with some reasonable and helpful things that we might do with our code optimization-wise. But first, we need to recall a couple of key concepts. So we will recall translation units, we will recall declaration definition, and we will recall storage duration and linkage before diving into the core of the talk. So let's start simple. Let's start with how our C++ programs are built. So we have a couple of CPP files, and we include a couple of header files. And first, what we do is we, during our compilation, the preprocessor is run, and the preprocessor prepares for us translation units, which preprocess all the includes, and we actually have this kind of huge independent translation units which are compiled in parallel, and they do not interact with each other. This is really important to keep in mind during this talk. So then we compile those translation units, and we'll have our object files. Then we'll link our object files together, and we will have final program, final artifact of the build, whatever it is, an executable, a library, whatever. So I guess who is familiar with this process? I just want you to stretch your hands, because after the break, okay, yes, of course, it's kind of basic. Now let's talk about declaration and definition. Now this, ladies and gentlemen, is function declaration, as you might know. In order for us to have a function definition, we actually need to include the body of the function. Now we have function declaration and we have function definition. All right, no surprises there. Now this statement is actually a variable definition. This statement defines a variable. But there are ways in C++ to actually declare a variable without defining it. Any ideas? How would we declare? Please. So how do we? No, I think actually during the talk, no, Mike, but just feel free to participate in the conversation, and that's how I want this talk to be carried through. So how do we make variable declaration? Ideas? Yes?
Maybe with extern?
Yes, exactly. One way is with extern, the keyword extern. Another way? That's a little bit tricky. Not really. So yes, we can use extern, and we can use non-const static data member, which in fact actually declares a variable, and if we want to use it, we need to define it elsewhere, for instance in a CPP file corresponding to this header. So what do we know about declaration definitions? We can have arbitrary number of declarations of the same entity, but we have to have exactly one definition in one translation unit, and sometimes, under certain conditions, we can have more definitions in different translation units of the same entity, but all of the definitions have to be the same. This is one definition rule, ODR. If they are not the same, we have problems, all right? Not sure if we have a way to resolve this undefined behavior in upcoming C++ 20-ish. No? No? All right. Okay, now let's talk about linkage. We have this simple program. In BCPP, we declare function SQR, which we use in function check. And then in ACPP, we define function SQR. And everything works. This program works because this function defined in ACPP, this symbol, has external linkage, meaning it will be available for the linker on the link step. So if you try to compile this program, it works. If we ask the compiler to explicitly generate object files for us and then inspect these object files with a tool like nm, then compiler will list all, or linker or whatever, list all the symbols that exist in this object file. And we can see that in b.o, which corresponds to BCPP, we have function SQR marked with u, meaning the symbol is undefined. So compiler knows that the symbol, it is declared in B and it exists somewhere. We can use it, but we just don't know where it is. But we are promised that we will find it. And then in ACPP, in generated a.o file object, we have the symbol SQR t, meaning text. We have code. We have actual definition of this of the symbol. Everything works. Great. All right. Now, what changes if we add keyword static to this function in a CPP file? Of course, this won't longer work because in this case, SQR will have internal linkage, meaning it won't be exposed outside of this translation unit, and linker won't be able to find it. So if we inspect this file from A, we don't see anything because nothing is exported from this file. And we have this infamous error, undefined reference to something. I do believe that most of you experienced this error more than once in your life. So what is linkage? Linkage is a concept that defines where a particular entity can be referred from. If an entity has no linkage, then you can only refer to it from its current scope, let's say automatic variables. If it has internal linkage, you can refer to it from the current translation unit, let's say this static functions defined in this CPP file. If an entity has external linkage, you can actually use it from all the other translation units. And there is also a notion of external weak linkage, that meaning that the entity might be defined in multiple translation units, given that all definitions are the same, ODR implied. And here's an asterisk here saying that this is not actually in the standard, because indeed in the standard you don't find this concept of external weak linkage. But to my knowledge, every linker in existence actually implements this and uses this as this external weak linkage. You can inspect for it. And we also have module linkage, which basically says that we can refer to the entity from the same module unit or other translation units of the same name module. I just read it verbatim because I'm not a huge fan of modules, to be honest, and we won't cover them. Sorry, and we won't cover them during this talk. Basically, you can everything will apply within a single module, or you can consider your program as having just one module, as it usually is. Now let's talk a little bit about storage duration. Just some simple function. We have a local variable here, and we know that this variable will be created and it will be initialized every time we enter the function. Just normal behavior, and this function will always return false. So this entity counter has automatic storage duration. Now, let's say we add this keyword static to this function. Now, the storage duration of this variable changes to static, and now we know that this variable will be created and initialized only once upon the first the first call of this function. And then the function will return false for first two times, and then it will return true. So this is storage duration and how it affects, let's say, local variables. So what is storage duration? This is a concept which is applicable to objects because it involves actual memory somewhere during runtime. When we have an automatic storage duration, we can reason that this storage for the object is allocated when we enter the scope, and it is deallocated when we leave the scope. I mean, of course, in reality, it might be a little bit different because of the optimization and inline and stuff, but generally, it will happen as if it was true, as it always true for the optimization involved. For the static variables, for the static storage duration, storage allocated, deallocated when begins, ends. For thread, when thread begins, ends. And for dynamic storage duration, meaning the object that we allocate with new and we deallocate with delete, well, basically the allocation and allocation happens at the moment that when we call new and delete. So this is only applicable to objects. And the rules specify the times of allocation and deallocation of the storage of the object. They do not say anything about initialization of the object because, as you might know, initialization in C++ is complicated, especially for global symbols. Storage duration and linkage to the degree is defined by keywords called storage class specifiers, which are static, extern, thread local, and mutable, which is kind of strange. Because mutable affects neither linkage nor storage duration, and it's not completely clear to me why it is called a storage class specifier, but whatever. We will be talking about static, extern, and thread local, the big ones. And the keyword static, as you might know, and as you might have mentioned, dependent on the context, it might affect linkage or it might affect storage duration. Just so you don't feel too relaxed because it's C++, we have to keep you alert, okay? So let's think about possible combinations of the two. We have some linkage, we have storage duration. Since we're talking about storage duration, we are only concerned with objects, okay? Let's say it's an object with automatic storage duration. It is a local variable. If it's a local variable, then by definition, it will have no linkage because there is simply no syntactical way to refer to it from anywhere outside of its scope. So no linkage for automatic variables. For dynamic variables, again, they are created on the fly, and the only way you can refer to them is through pointers. So we may reason about the linkage of a pointer, but we cannot reason about the linkage of a dynamic object that we've created. So naturally, during this talk, we will concentrate only on objects with static and thread storage duration. And these guys might have all the linkage. And the thing is that actually you better have control over the linkage because it might be beneficial to better express your intent and to have more efficient programs, which run more consistent programs, as we will see from the following examples. Okay, by the way, if you have any questions or just something you want to clarify, just raise your hand, please. Or yes, please. Jose, maybe I. Okay, all right. So, all right.
Thank you. On the external linkage for the thread local, how do you get access to a thread local variable? Because it doesn't have any sense, isn't it? Because I don't see how you can have something that's thread local and then you have access from another compiling unit.
Oh, these are pretty orthogonal. I mean, you have, it just says if you can access something from this translation unit, you can access this from another translation unit. They will be together in a single program.
Oh, but you don't have access from, for instance, if you have another thread, you cannot have access to this variable that's in the other thread, I want to say, no?
No, you can. You have to protect it, of course. You have to make sure it is synchronized, but you can have access to a variable itself. And then if it's an atomic variable, let's say, we have in a header file, we have thread local atomic variable, which will be available from all translation units. No problem with that.
I'm not seeing it because, for instance, if you have 5 threads, each thread has a global thread local. You cannot access from another thread the global.
Yes, exactly. I mean, if you have thread local, it is thread local. You cannot access from another threads, but you can access it from different translation units.
Oh, okay. But it is in the same thread, you want to say?
It is in the same thread. Okay. It will be the same variable in the same thread, exactly. Yeah. Okay. And probably atomic, actually, it's not needed here. That's a strange remark from me, because it's thread local. You don't have to synchronize it. Okay. Yeah, let's move on. Let's identify the storage duration of an object since we're interested in its storage duration. How do we do that? Thread local is a good word. Whenever we see thread local, it doesn't play game with us. If we see it, we might be sure this is thread local storage duration. If we don't see thread local on our entity, then let's inspect its scope. Is it a global scope, namespace scope? Then it will have static storage duration. If not, all right, let's see if it's declared on a in a block somewhere in the function, or it's a member of a class. Then let's look for the static keyword. We see static keyword, okay, it's going to be static. Again, if static was applied to a variable in global namespace, that would alter its linkage. Okay, that's why static is context dependent. And if we don't see any of those, then we have a variable with automatic storage duration. So actually, I'm pretty sure you already knew all these rules and you applied them many times, but maybe you didn't have them in one place. If you want, here they are in one place. All right, now let's try to actually apply our recalled knowledge of how it works. And let's take a look at this program. So we have 2 files, ACP and BCPP, and everything they do, they just include a single common header, common H. The question is simple. How do you think, will this program compile or not? And if not, why not? Linkage? Yeah, okay, it will build. Okay, compile plus linking. That's important notice. Compilation plus linking. If it's going to build or not. All right, so what might we expect? What might be the problem here is that we will obviously have these the same names actually defined, because these are variable definitions, right? The state variable definitions, and we have these variables defined in 2 different translation units. And the question is this okay? All right. Is this okay or not? And if you try to build it, then we will have, yes, we will have an error. Multiple definition of symbol name. However, we will have only one linker error. We won't have complaints about symbol, about variable price. Why do you think is that? But name is also const. No, it's not. It's not. Actually, it's not. Actually, it's not, because const is to the left of the asterisk, which doesn't make the price const, of course. The name const. It makes the const. This is the pointer to const, but the pointer itself, name, is not const, obviously. All right. And we have a rule just specifying that any form have internal linkage the const qualified type. So const qualified global objects by default have internal linkage, meaning that these symbols won't conflict with each other. because they will be included in both translation units, but they will have internal linkage. So they will be encapsulated in the respective translation units, no problems. All right, internal external linkage. Now, let's modify it a little bit. Constexpr and const. Who will think this will compile? 1, 2. You're expecting some catch, right? Yeah. No catch here. It will compile because these are basically the same. Constexpr for an object declaration implies const, so they both are kind of const for the compiler, and both will have internal linkage. They will be encapsulated. No problems with that. Another question. So what we do here, we have a constexpr. Do you have any question? Maybe you want to ask something? No? Okay. What we have here, we are essentially running a program that checks if this object, which is defined in the common header file, and which is present in 2 independent translation units, is it in fact a same object or not? Because here in function main, we'll take an address of the variable price, which is in current translation unit, and we call function price b, which takes the address of the variable from another translation unit. Okay? So we're comparing these objects. And now, who thinks these are the same object? Who thinks these are the different objects? All right, following so far. Glad you guys, because this object, constexpr, const internal linkage, all right, 0, they are not equal. These are essentially, and here you might actually have the first sensation. Okay, we have this object which seems kind of single thing, but it actually exists in multiple incarnations in our different translation. Maybe it's not good. Maybe it's not good for the optimizer. Maybe it's not good for the semantics and for the size of the binaries that we produce. Maybe we can do something about it. So this is another definition of the price. Now, who thinks that now we will have a single object in all translation units? Yeah, so the comparison will sound true. All right, still different. All right, we have participation rate around 30%, and that's pretty good. If keyword inline is applied for a global variable, then it implies external weak linkage, meaning this, we have external linkage, so they will be exposed from different translation units, but linker will assume that all definitions are the same. It will pick a random one, whatever, because it assumes they're all the same. And this will indeed be a single object, because they exist, of course, as different objects during translation in translation unit. Otherwise, it's just impossible with a regular C++ build. But then they are merged during the link phase. And in the final program, we have a single object, which is pretty good. Maybe it's not that important for a simple double, but it's pretty important for larger objects, as you might imagine. Okay, so here are some quote that governs inline. You see that internal linkage, const qualified, unless they are inline, in which case this is not longer internal linkage. This is something else. Standard doesn't say about external weak linkage, but basically it says, yeah, it's we may have multiple definitions, but they all have to be the same. And if we inspect the object file generated by these files, we'll have that this price marked with V, which says symbol is a weak object, so the linker explicitly tells you that's a weak object. Okay, so here's another way to resolve this problem. As we've said, if you want to change the definition of a variable to the declaration of a variable, we might use extern. And that's exactly what we did here. So now price is not defined in a common header file, it is only declared in the common header file. And it is defined in one of the files. And again, it works. The symbol has external linkage, and we separated declaration and definition of the symbol. And since we don't have declaration or definition in the header, no problems. So again, as expected, these are equal. Okay, now let's talk about functions. We have the definition of a function in a common header file. Who thinks this will compile and build successfully, no linker errors? A couple of people. Expecting linker errors? Some linker, yeah, good, of course, yeah. This will be a linker because, yeah, we have multiple definitions. What are you going to do about that? Now, let's say we have a constexpr function. It's still not inline, as you might have expected, but it's constexpr. What about that? Who thinks it will compile and build? Okay, who expects any problems with that? A couple of skeptics, right, good. It will work because, well, at least for this case, in C++, we have a sensible default rule that constexpr for function declaration, this is constexpr, so it is expected to be available to all the translation units during compile time. Otherwise, there's actually no way to use it in constexpr context, right? But if we have a function which has to be constexpr, then we probably have to place it in a header file. Okay, let's just make it inline by default. And that's a sensible default. So it will work. All right, and the final example from this little quiz block for you. So imagine a situation, it actually happened to someone, to me, definitely. So let's see, I develop file main.cpp. I have my local task in this file, and I declare a local class called local for that, which I'm necessary for this to solve this particular task. And I call it local, and I declare a function foo on it, static function foo. And then my teammate, actually working in the same project, it uses another file, other CPP, and they also have some tasks they have to solve. And they invent a local class for that and call it local. And the class, and just by coincidence, we use the same name for a class and a function. And then we build everything together and we run our program. Who thinks that we actually will have expected output of main other? Yes, who thinks we won't have expected output? Okay, who thinks we're not guaranteed anything? Just anything can happen. Yes, our favorite part of the language, anything can happen, because we do have multiple definitions of the same. This object is considered the same, it is named the same. But these are different. This is ODR violation. And if you play with the options, I was not able to reproduce this in Compile Explorer, unfortunately, but I definitely saw it in my local build. With the particular options, with the particular compiler, you might get something like this. Yeah, because linker sees two symbols, it discards one, it's only left with another. It just happens to be main in this case. But generally, it's undefined behavior, nothing can happen. Anything can happen. Okay, so now these have external linkage. How do we fix that? Yes, exactly. It's just a thing developed specifically for that. Just put everything in anonymous or unnamed namespace in your CPP file that you don't want to stick out from your CPP file. That's a really, really sensible thing to do. Just, is it going to be observable outside? No, just anonymous namespace. I don't care. You live here. This thing will work as expected. Saying about anonymous namespace. Now these guys have internal linkage because it is within anonymous namespace. And even if you try stuff like declaring something extern within anonymous namespace, no luck. Anonymous namespace will beat everything. So some quotation, what's important here? It actually, it says, what do we do with ODR violation? How do we handle it? And each definition consists of, this is the definition of what is the same representation of a symbol, same sequence of tokens, okay. And the last part is the most interesting. If all these requirements are satisfied, the program behaves as if there is no definition. That's good. Otherwise, the program is ill-formed, no diagnostic required. So it's not about undefined behavior, to be honest. The thing is, it's not a program with undefined behavior. This is not a program, period. We've written some text, and according to the C++ standard, this text is not a program, because program is something well-formed, and we have something ill-formed. the compiler says, okay, whatever, I don't know what it is. Surely this is not a program, but I will try to compile it. I will produce something. You do whatever with it. Probably it won't work what you want, but yeah, you try your chances. And this is amazing. So this, I think, is like meta level above undefined behavior. It's not undefined behavior, it's just, I don't know what's happening, but here are your program. It's just, I don't know. And so if I understand correctly, okay, that's a philosophy, let's not dig into that. Now, a couple of words about templates. First, I wanted to say a lot of words about templates, but then I decided, this is pretty, like, the rabbit hole is really deep, You don't want to go there. So I will just state a couple of statements that I think will help you to guide you through your programming experience. First, so we have templates, we have functions, variables, classes, and let's remember that there is no such thing as a template entity. There is only an entity template. So we have a variable template. We don't have template variables. We have variable templates. We don't have template functions. We have function templates. Why this is important? Because, like, a template of an entity is something on another level from an entity. A template function is not a function. Like a function template, sorry. Function template is not a function. And a variable template is not a variable. It's a template from which we can produce a variable or function during the process called instantiation. Okay? And even though there is a notion of linkage for a template itself, and there are keywords, specifiers applicable to the template itself, it doesn't make much practical sense to talk about the linkage of a template. But it makes perfect sense to talk about linkage of instantiated entity. So it is convenient to think that specifiers apply to instantiated entity, not a template itself. It's a very good rule, it never failed me. And the thing is that the linkage of implicit instantiation is not always thoroughly defined or implemented, meaning we might have some rules in the standard, and actually there is a defect report from 2019 about exactly that, about linkage of implicitly instantiated template variable, which was just recently implemented in GCC 15, which is not even released yet, like 5 years later. This was 2024, 5 years later. So just please don't, the standard says something about the linkage of those guys, but don't assume anything, because even if standard is specific, which it's not always is, compiler might fail you. So the recommendation is really simple. It's just whenever you have a template entity variables, let's say, just set your linkage explicitly. If you have a variable in a header file, just declare it inline to be sure it has external weak linkage. If you have a template variable in a CPP file and you don't want to stick it from the file, just either put it in an anonymous namespace or make it static to make sure it has internal linkage. All right. Now let's talk about how to declare a constant, because that's not an easy topic. But I think we're ready. I don't cover all the cases, but in most of the cases we declare a constant. And the thing is, as you might probably already understand, we actually want to know the linkage of the object that we create. And we need to pick it properly. And basically, we just need to get the proper combination of these guys. All right? So now let's see. We have a constant with an initializer in our header file. If we can make anything constexpr, just let's make it constexpr, because like see previous talk, constexpr is great. If you can have anything constexpr, just make it. But to make sure that the linkage of the variable is correct, at inline we have external weak linkage. For the members of the class, if we have a constexpr static data member of a class, it is implicitly inline, which is not that easy to remember. So actually you might write static inline constexpr int, and most of the linters, they will say you, hey guy, it's just inline, it's actually redundant, you can remove it. But if you write inline there, no harm will be made. For non-literal types, which we cannot declare constexpr, we might still use const, in which case we have to explicitly write inline. Otherwise, it won't have the linkage we want. I believe it will have internal linkage in this case. And if we are within a CPP file, well, again, if you can, use a constexpr and put everything within an anonymous namespace. So constexpr, outside of an anonymous namespace will work. It will still have internal linkage, as we've seen in the examples. But if you put it within an anonymous namespace, no harm will be made. Okay? It still will be good. And exactly the same for the members of a class, of static members of a class. And now, if you can notice, we actually reached the point where we consider this local constexpr variable, which I claim you should declare static. So let's say we have a function, we have a local automatic constexpr int variable in. So who understands why it would make sense to make it static? What even will be affected in this case? Okay, that's, I hope it will be useful. So the thing to like a mental model, which is extremely simplified model of how C++ works, but again, it works every time in practice. Just imagine, that's how it actually happens. Our C++ programs, they run twice. Since the dawn of constexpr, it runs twice, like two independent programs with independent rules, with if consteval branches go into different directions. It's just two, in general, different programs. Okay? So constexpr makes sense, makes perfect sense at compile time. It has clear semantics. It says what it implies. But once we've done with that, it's just constexpr dies. There is no more constexpr, but it reburns as simple const. So now, if you want to reason about the runtime behavior of a program, which is a completely different program, by the way, then you just read constexpr as const for variables in this case. And now, another question is, imagine you have a const local variable in your function. Would it make sense to make this variable static? Who understands which effect static would have on this? Okay, at least now we have a couple of hands, which I believe, means that this is a helpful model. So let's take a look at the example. We have two functions, and they both declare constexpr local variable constant, v, and they both call another function bar, with this variable being an argument to this function. And as you can see, in foo1 we have static constexpr, in foo2 we have simple constexpr, no static. And the assembly code, you don't have to know assembly, you just see it is exactly the same. So what's the point? No point yet. And now I will add one character in the declaration of function bar. What do you think this character would be? Ampersand. Exactly. Okay, actually that counts, sorry. But the important part, I added the ampersand. And what happened now? We have this function bar, and we don't have the definition of this function, we only have its declaration, meaning the compiler cannot see through this function. It doesn't know what's going to happen with this object, but what it's being told that the function expects the object being passed by reference, essentially by pointer, meaning that we actually need the physical address of this object, and we need the physical object to be able to pass it to this function. So what happens now? In foo1, take a look at the assembly of foo1. It didn't change much, did it? Because the object of which it takes address already exists. This is a static object. It exists somewhere here in read-only section, where all the static objects live. So it can simply refer to this particular object. But in function foo2, even though the variable is constexpr, but now we're at runtime, really. So we forget about constexpr, what we see is const variable. And now we have a reference to this const variable, so we need to have a physical object. and compiler forced to create a physical object, which it does. You see push, you see pop, so something's being created on the stack. And by the way, the tail call optimization failed because we need to clean up this function. All right, so this is the difference. That's why we really want to make our constexpr a constant also static. And by the way, it actually better communicates your intention. Static means just it doesn't depend on anything. It doesn't change during the execution of the program. Constexpr tells you about the compile time, static tells you about the runtime. And yeah, another remark about const and volatile. Who can say that they actually understand what is a const volatile variable? Like both of CV qualifiers, both of them. One hand, two. Okay, yes, a couple of hands, right? Yeah, that's good. And the thing is, it might sound a little bit strange, but actually, const and volatile, they are about completely different things. They are orthogonal. So what const means, it answers the question, can we, within our program, can we modify this object? And volatile says, can someone else outside of our program modify or read this object, can have access to this object? So it's perfectly fine to have a const volatile object if it's mapped to a particular address in some embedded device and some external bus, let's say, changes this location in memory, and we can read, but we are not supposed to change this value from within our program. This is going to be a const volatile variable. Okay, consteval and constinit. We have, how many time? How much time? Oh, okay, this is good. We have some time. Let's talk a little bit about consteval and constinit. So what is consteval? Consteval, actually, I have to confess, I do have troubles with constexpr functions because they are not truly constexpr, while constexpr variables, they are truly constexpr. If you have a constexpr variable, you know it is going to be available and computed as compile time, but if you have a constexpr function, you're not guaranteed, and it actually might not be that easy to understand. So apparently at some point, like the smart people from C++ committee said, okay, yeah, that's actually not convenient, you know. I was like, yeah, you know. What if we make sure that a function is only will be executed at compile time, and then we have consteval function. And there is a simple example demonstrating that. So consteval expr, a consteval function, a consteval specifier implies constexpr because, well, definitely going to be available at compile time. So yeah, it can be used in a particular context. A constexpr function, in these two invocations, one is happening at runtime, another is happening at compile time. Both work fine, no problem. If you have a consteval function and we try to use it in runtime context, it just doesn't work. I would expect that that's how constexpr function would behave, but that's not what we have. And we don't have consteval variables, by the way, because these are constexpr. Well, okay, I personally think that's a mess, but maybe someone can prove me wrong. So it's convenient to think that the consteval function, immediate function, it only it is not available at link time and runtime. It's only available at compile time, and it doesn't produce a symbol and object. While in fact it might, because as you probably know, the CPP standard, it doesn't distinguish compile time and runtime. It only defines the result of the execution of a program in terms of C++ abstract machine. So the wording for consteval function is a little bit tricky, just to make it appear as it is only available at compile time, and it kind of works. So it's something that might be perceived as a functional macro, actually. And that's, again, that's a helpful model. Maybe there are some use cases in which you can actually observe a consteval function in an object file. I'm not aware of those, no, but maybe generally it might happen. I would love to see those, if those exist. And something about constinit. So imagine what we have here. We have some function-enable logger. We have logger-enable class, which is when we create the global global instance of this object to make sure this functionable logger is called before we enter main. So we're interested in logging while initialization of some static objects. And it goes and it sets basically this atomic variable to true, while it is initially false. But the problem is, who is aware of this thing called static initialization order fiasco in C++? Yeah, a lot of you. So basically, when we have global objects listed within one CPP file, we know that they are initialized in order. But if we have them in different CPP files, they are initialized somehow. We don't know. The order is not specified. So generally, we are not sure at which point this logger-enabled variable is initialized. Maybe first we call the function enable logger, sets as a true, and after that is initialized to false. We don't really want that to happen. So, and in order to make sure that the behavior of the program before the program actually started the execution is correct, we add this constinit specifier to the logger-enabled variable. And what this means that it is like an assertion. This statement asserts, this specifier asserts that a variable has static initialization, and static initialization is happening. There are like multiple phases of static initialization in C++, and static initialization it's something independent of each other. It's like default values of the object, which is really safe to call. And then we call the constructor of an object, and this is a like later state of the initialization. So if something can be declared with constinit, then we are guaranteed that we won't face static initialization or the fiasco. And it's obviously only applicable to variables with static and thread storage duration, because we don't have such problems with variables with automatic storage duration. The funny thing is that constinit does not imply const, and that's the thing. We can enable and disable logger during the runtime. So this variable is not const. We can change it, and we do change it from the constructor of logger enabler. So it's a bit strange word, again, but yeah, actually it serves this job, which is good. Okay, so now I think we're ready to tackle the initial example, right? This is the example, but before going to that, I think it might be helpful to actually summarize of the knowledge of the interaction of the specifiers in C++ and how they affect linkage of different kind of entities. So we're not going to go through all of this table right now, but you can refer to it. The important thing to us is that we can like pick a proper column and then go line by line and see what is the resultant linkage. And let's start with const. Now we have at line number 3, we have a global variable, right? So we go down the column global variable. We see that by default global variables have external linkage. Then we see that constexpr implies const, and now we have const. And then line 5, we see that const implies internal linkage. Okay. So what we can tell that first const is redundant; it is implied by const, and yeah, we can let's say it's static, and let's take a look at static and inline, and we see that static is actually goes after inline. Okay, so if you have both static and inline, then static has a stronger hand. It disables inline, so we can just remove inline. And what we have now, we have static, which, as we know, for global variables implies internal linkage. And we have thread local, and we know this makes this variable to have thread local storage duration. And we've already learned about const and volatile. And yeah, by the way, this variable is template. But what we are left with is a constexpr volatile variable template with thread storage duration and internal linkage. And we're done here. So this is our example untangled. I don't guarantee that this is like really easy to understand. What exactly does it mean? But now at least we can reason about it with all the context that we've got with this talk. I'm not sure this is used once anywhere in the real world. It would be really fun to see. I don't know. Should be some modern embedded code because const are volatile. Doing some, I should ask guys from Emba++. Okay, so some conclusion. There are actually pretty simple recommendations to you. First, use inline for variables and headers to ensure external weak linkage. Put stuff into anonymous namespace in CPP files because you don't want accidental ODR violations in your code. Prefer constexpr over const whenever possible because it is convenient and because you will have additional checks on compile time. And then mark local constexpr variables as static to make sure that no extra objects are created during the runtime. With that, thank you very much. Any questions?
Questions?
It's one over there.
Question about one of the recommendations. So you say you advise to use inline for variables and headers.
Yes.
What will happen if you have same variable with the same name and two different headers? Is it not a source of some mistakes?
Yes, definitely. This will be a source of mistakes. This is true if you have like name collision. Then you will. So you mean like completely different variables, right? Probably the different type. Just they happen to have.
No, it's even the same type. So let's say you have two integers I.
Okay.
In two different header files, you set them in line, you initialize them to different values.
Yes, this will be ODR violation, and this will probably this won't probably be diagnosed by the linker because yeah, it will assume that this is in fact a single variable. So you're correct, maybe in a sense that if they had internal linkage, that maybe in this case it would be easier for linker to determine that this is actually a name collision. So yeah, I agree. This might be a situation. Yeah, thanks.
What's the minimum C++ standard required to do static constexpr in local functions, like the last one?
Because generally it's not a constexpr function, so I think maybe C++11 is even enough. If you want to have a static constexpr, I'm not sure, but if you want to do it for a constexpr function and have static constexpr and constexpr function, you probably need C++23. But for non-constexpr function, I think C++11 should do.
Okay. And I didn't get the constinit thing, like.
Oh no, that's C++20, I believe.
No, I didn't understand. Like, could you go over the?
Oh, just the question how
yeah.
constinit works.
Yeah.
Okay, yeah, sure. Constinit. So, all right, what? You see, we have two global objects. Yeah. One global object is logger enabled, and another global object is the logger enabler, which runs its constructor when the object is created. So imagine that, and since these objects are global, the standard does not guarantee in which order they're going to be initialized. But initialization of static objects happening in multiple phases. Maybe I'm not sure about like all the phases, but one is static initialization and zero initialization, and another is dynamic initialization of global objects. So if everything that is initialized during static initialization, it is basically initialized with constants. So no dependencies, no code run, it's very, very simple. And we know that the constructor of logger enable will run during dynamic initialization. And it references other variables, in this case, logger enable. But since when we apply constinit to that, we might be sure that it will be initialized during static initialization phase. It won't compile. It won't compile. Yeah, exactly.
It's not constant to the right. It's calling the functions.
Yes. Yes. Yes.
So I think it's Nico Yosutis who has in one of the book that constinit is essentially constexpr minus const. And I think this is a very simple definition of the thing.
That's a good one. I should include it.
Yes, I have a question about the last example that we did, which is the same as the one at the beginning.
In the beginning.
No, it's the last one works. It's the same one, I believe.
That we untangled.
Yes, this one. My question is, because at least maybe I'm mistaken, but I recall that you mentioned that variable templates are different to the instantiations, and that the variable templates can have qualifiers to themselves. So if I were to instantiate, make an instantiation of this template, which qualifiers would carry over to the instantiation?
So exactly. So when you do an instantiation, what you do, you throw out this template thing, and you can, like, all the keywords, let's say specifiers and qualifiers, they will transfer to your instantiated entity. And that's why if you spell your keywords explicitly, you might be sure they will be transferred to the instantiated entity. The recommendation is you really want to have those, because if they are not present, you will have with some default, you will end up with some default behavior, which might not always be even well defined and might not be what you want. Okay? Again, these specifiers and qualifiers, they do also apply to the template itself, but this knowledge of, let's say, linkage of a template, I don't find it very useful. So there are, of course, there are some edge cases, sure, and probably you guys can tell me some of those, but generally I don't think they are that useful to reason about.
Okay, thank you.
Hi, so in a threaded program, would adding static can result in some overhead, like for a local variable, because it guarantees that a variable is initialized only once per all of the threads?
Generally it might happen. However, it's just every decent compiler that sees that a variable is constexpr, and its value, so basically it will generate it in text section, and it would put some value there. And I'm pretty sure you cannot, like, maybe with minus o minus 1, stuff like that, you might have a lock there that actually checks. But if the value of a variable is available at compile time, I cannot imagine that a compiler won't be able to use it and put it in static storage.
Okay, thank you.
Thank you. More questions? Up.
Okay, so maybe it's a useless question, but is there any reason to put the assignment in that definition?
Sorry, what's the question again?
If makes any difference if you remove the equal mark in the definition?
No, I believe nothing will change.
Okay, yeah, your preference.
Yeah, it's just, okay. I do love to initialize my variables with equal sign. It's just maybe some personal quirk. But I don't love when the braces or brackets stick to the variable name. It just makes me feel uncomfortable.
Well, in some cases, there might be a slight difference depending if type T has a explicit constructor or not.
Maybe you're right, even though I think that this particular case, when the braces are empty, if there is difference between equals empty braces and simply empty braces, this might be the case. I might investigate that. Yeah.
Yeah, just want to. Can you please go to slide 32?
Which one?
32.
32. Yes.
So this is a mistake I personally made. The inline is not implied there if the compiler is like older than 17. So for static const exp n equals to 5, that the inline is only implied if it's like 14, C++ 14.
Oh, so it's not implied in C++ 11.
In certain cases, it's not. If it's in ODR use, you need a definition outside of.
Okay, yeah, thank you. So the comment is that for line for a static data member, static construction int n equals 5, that it will be implicitly in line only starting with C++ 14. 17. Maybe because there were no inline variables before C++ 17. Yeah, this is correct. So yeah, everything here applies to C++ 20, and when it comes to different standards, yeah, of course you have to watch out. Yeah, the behavior might be a little bit different.
In some cases, the compiler won't complain. So the compiler or linker will complain only if the n is in ODR use. That's why I was a bit surprised when I saw that issue.
Okay,
like,
yeah.
Kind of like sometimes it works like inline, sometimes it doesn't. But technically, it's not.
Yeah. So basically, the recommendation is to use modern compiler. Yes. Thanks.
Any other question?
Yeah. So just to be clear, should we use a non-static constexpr variable inside a function? Like, from what you said, I don't see a reason not to use a static constexpr variable in a local scope.
There might be some really tricky case where, for some reason, you actually don't want this variable to be present in your text section of a binary, or you don't want to have a pointer to this section, maybe something behind these lines. Generally, I would say this is a really good default recommendation, but I think for the most recommendations in C++, there are some really quirky edge cases that sometimes you won't deviate from those.
Okay, thank you, because I faced this dilemma like a bunch of times, and I was never sure if I had to put static or not. So that's a good recommendation. Thank you.
Yeah. If you have a strong use case where static would do harm, I would love to hear about that.
Okay. Any other question? So thank you very much, Mikhail, and let's go for lunch. By the way, the room will be locked over lunch. So if you want to leave things here, just know that it will be closed for 90 minutes. Thank you.
Yep.